All right, so we are going to play more with rate today. This actually is going to be really, really, really similar than what we did yesterday. So there's not a lot to it, which is kind of nice. We're not going to learn a whole lot more. We are going to learn how to graph these things. We're going to look at the graphs and kind of see what they look like. And then we're going to play with these things. So Pauline mows a lawn at a constant rate. Good for her, because that's seriously hard to do, right? Like bumps and dips and whatever. Suppose she mows a 35 square foot lawn in 2.5 minutes, which is really a tiny lawn, but she's also mowing it crazy fast. So it's probably kind of reasonable. What area in square feet can she mow in 10 minutes? What about in T minutes? So, okay, so let's think about this. I think it's actually easier to start with the T minutes and to set up our equation and then figure out how much she can mow in 10 minutes. So the area, 35 square feet, that's the area, right? Woo, I forgot how to write. And she can mow that in 2.5 minutes. So that's the time, right? So we know what's the rate. The rate is the area divided by the time. How much can she do in a unit of time? In this case, it's going to be in a minute. How much can she mow in 1 minute? Okay, so we're going to say 35 square feet. So square feet, so there's a foot with a little square, per 2.5 minutes. So every 2.5 minutes, she can mow 35 square feet. So I'm going to whip up my calculator and say, okay, 35 divided by 2.5. And this will give me my rate. How many square feet per 1 minute? Ooh, 14. That's a nice number. So she could mow at the rate of 14 square feet per minute. So every minute she mows 14 square feet. So how many does she mow after 10 minutes, right? So this is how many in T minutes. This is how many, okay, so let's do, so the area, remember the area is going to be equal to the rate times the time. If we look at it, we forget, okay, is it rate times time? Is it rate times area? If I don't do this as a slashy one, if I say 14 feet, square feet, divided by per 1 minute, I can express it as a fraction. Well, if I multiply that by time, if I multiply that by minutes, I've got minutes divided by minutes and it goes away and my answer is in area. So it's how you can think about it, okay? So if I multiply the rate times the time, right? I have rate times the time. I don't know what the time is, but I know it's in minutes. Then the minutes go away and I'm left with feet, okay? So area equals rate times time. Well, we know the rate, right? I don't need an R there. Area equals 14 T. I don't know what T is. So that's our general linear equation. Area equals 14 T. And it's a linear equation. We're going to talk about that in a minute. So how much does she mow after 10 minutes? So I'm just going to substitute in 10 for T. So the area is going to equal 14 times 10 minutes. So 14 square feet per minute times 10 minutes, that equals 140 square feet. So if your front lawn is 140 square feet, which is really quite small, you could do square feet or foot squared, doesn't matter which, but she can mow it in 10 minutes. So I'm going to circle my answer there and I'm going to circle my answer there. But now I need to fill in this graph, okay, or this chart. And it says time in minutes. And on these, what we're going to do is we're just going to type in some random times. So if we were in class together, I'd have you guys give me random times, but we're not. So after 0 minutes, how much has she mowed? After, okay, so I'm going to look at this graph because we're going to graph this. It only goes up to 7. So I'm not going to go any higher than 7. After 2 minutes, how much has she mowed? After 3 minutes, how much has she mowed? After 5 minutes, how much has she mowed? After 7 minutes, how much has she mowed? So let's see. So the area, I'm going to go back to the pen. Area equals 14t. Well, t is 0. Area equals 14 times 0. Now, at time equals 0, she hasn't started yet, right? So this is a dumb question. It's going to sound dumb. How much have you mowed before you start? Well, I mean, of course, it's nothing, right? So 14 times 0 is 0. And sure enough, that totally makes sense. When the time equals 0, she hasn't mowed anything. But now I'm going to graph it because we have a dependent variable and we have an independent variable. The independent variable is time. Time is going to keep marching on no matter what. There's a song, time keeps on slipping, slipping, slipping into the future. And there's nothing you can do about it and there's nothing you can change it. But can we change how much lawn we're mowing? Right now I am mowing no lawn. None. No lawn is being mowed at my house or at anybody's house by me right now. So that's the dependent. Even though the time's marching on, I'm not mowing lawn, right? Pauline here is mowing lawn at the rate 35 square feet in 2.5 minutes, 14 square feet a minute. She's mowing lawn. How much lawn is she mowed? She's mowing lawn depending on the time. So X is always your independent variable. Y is always your dependent variable. So it says time in minutes T. Okay, so T, that's not X, but it's still going to be on the X-axis. So at 0 minutes, she has mowed 0 lawn, which is such the duh of the world. Of course, she hasn't mowed any lawn at time equals 0 because she hasn't started, okay? So what about after 2 minutes? Now she's mowed some lawn, right? She hasn't mowed a lot of lawn because it's only been 2 minutes, but let's see how much lawn she's mowed. We know that she's mowing at 14 square feet a minute. That's our rate. Our rate doesn't change because she's mowing at a constant rate. She's some kind of constant rate superhero because I can't do that, but go Pauline. Times 2 minutes. Well, what's 14 times 2? That's 28. I can do that math in my head. So at 2 minutes, when X equals 2, Y equals 28. So at 2 minutes, she's mowed 28. Now, I have 25 here and I have 30 here. So I kind of have to eyeball it and kind of be close and boom, there you go. Is it perfect? Probably not. Do I care? Probably not. Okay. So at time equals 3, after 3 minutes, how much has she mowed? The area is 14 square feet per minute times 3 minutes, right? Well, what's 14 times 3? That's actually the same as 7 times 6. So now she's mowed 42 square feet. So at time equals 3, she's mowed 42 square feet. Right there, precisely at that point is 42-ish. Ish, right? So after 5 minutes, how much lawn has she mowed? Area equals 14 times 5. 14 times 5 is 70. So after 5 minutes, she has mowed 70 square feet. So I go over to here, time is 5, 70. Oh, we are off the chart. I'm going to call it like right there. And then after, I'm going to change that 7 to one that's a little bit smaller so that I'm not maybe off the chart. Okay. What if I change it to, let's see, we've done 2, 3, let's do 4. 4. We could do 4. We could do, we do a fraction. Let's do a fraction. You don't have to do fractions. I'm going to do 2.5. Okay. After 2.5 minutes, how much has she mowed? So the area, does it work with fractions? Yes. Can you use a calculator if you don't want to multiply your fractions? Yes. 14 times 2.5, okay? And that is going to be actually 35. I just need to see. So 2.5, and it's precisely 2.5 right there. We go up to 35. Now, here's the deal. We're going to do a does it make sense test, okay? Because this is, what kind of equation is it? It is a linear equation. And what do we know about linear equations? They make straight lines. So can I draw a line and connect all my dots? Yes. Well, let's see. Let's find out. I'm going to shape. Here's a line. Conveniently, I'm on a computer, so I can do this. Can I connect all my dots with a light now? Okay, so here's the deal. There's that one that's not connecting super well because I plotted it. Weird, right? Because remember, that was the one. Oh, I even plotted it at 4, not at 5. Look at that. I'm catching myself on a mistake. I got the height right, but look, I did it on 4, not on 5. Let's fix that. So 5 and 70, and it's right there on the line. So if you've done these right, they'll all end up in a line. So I could do math to figure out the answers to these, but I can also look at my graph. How much has she mowed after 3.5 minutes? I can just go up here and be like, oh, 3.5 minutes, it's pretty darn close to 48 right there. Am I going to be exact? No. Am I going to be close? Yes. So you can do it looking at the graph too. Let's move on. Let's do another one of these. We're going to do another example. Okay, water flows at a constant rate out of a faucet. This is a problem if you don't want it to. Suppose the volume of water that comes out in 3 minutes is 10.5 gallons. That's a really fast faucet. Like, I've had to fill up a 5-gallon bucket to water my cows when our cow waterer freezes over, which happens every winter. I cannot fill up a 5-gallon bucket in 3 minutes. So 3 minutes and 10.5 gallons, that is an impressive faucet. So how many gallons of water come out of the faucet in T minutes? And then we're going to graph these. Oh, and they give us numbers this time. 0, 1, 2, 3, and 4. Okay. First, we got to figure out the rate. And remember, we're always going to have time in the denominator. So it's going to be gallons divided by time. Because we know how much comes out in 3 minutes. We really want how much comes out in 1 minute because per means for each. How many gallons per minute am I getting? So I'm going to start with 10.5 gallons. Divided by 3. Oh, this is gallons. Got to remember my units. 3 minutes equals. Okay. Is this math I choose to do in my head? This is not math I choose to do in my head. 10.5 gallons divided by 3 minutes is 3.5 gallons. So 3.5 gallons per minute. So every minute, you're going to get 3.5 gallons of water out of this faucet. You had Dharma better hope that it's intentional and not a leak, because oh my gosh, you're gonna have to clean up a lot. Okay, so how many gallons of water come out of the faucet in T minutes? So the volume, we're gonna call it volume because V in gallons. The volume is gonna be equal to the rate, which is 3.5, times the time. Okay. And if we look at our units, when we do the rate times the time, those minutes are going to cancel out and we're going to end up with volume. Okay. But so volume equals 3.5 times T. So I'm going to write it right here so I remember. Volume equals 3.5 times T. So at T equals 0, filling up a bucket, right? I'm feeding my cows with this super faucet that I'm a little bit jealous of. Well, maybe it isn't. I'm trying to think if it takes me longer than a minute or two. I have to maybe time my faucet. I'm curious now. Okay, so the volume, before I started at time equals 0, I have just barely started, haven't really started. How much water is in my bucket? Well, duh, it's gonna be none, but let's see if we get that with the math. So volume equals 3.5, time is 0. How much water is in my bucket? None. 3.5 times 0 is 0. That one is kind of a duh. Sometimes we start with water in our bucket, and that's when we have like +5. That means you've started with water in your bucket. But we didn't. No water in my bucket, so I'm going to do a dot at 0. Okay. Let's see what happens at 1 minute. Volume equals 3.5 times 1. At 1 minute, we have 3.5 gallons per minute. So at 1 minute, we have 3.5 times 1, which is 3.5 gallons. That would make sense. So at 1 minute, I'm going to put a dot precisely at 3.5. Exactly, perfectly. And my dot is perfectly circular. And you guys wish you could make perfectly circular dots too, just like that. So not. Okay, so let's see what happens after 2 minutes. Volume is 3.5 times 2. After 2 minutes, I'm going to get 3.5. So that's going to be 7 gallons of water after 2 minutes. And we've already brought a bucket out for the cows because my bucket only holds 5 gallons. This one I can't be precise because I have a dot at 7. Okay. So volume equals 3.5 times 3. Now, I'm going to intentionally make a mistake. Okay. I'm just warning you just to show you something. Okay. 3.5 times 3, we're going to say that's 9. Let's say I forget how to math and I say that it's 9. So 3.5 times 3 is 9. Okay. All right. Then we're going to keep on mathing here. Volume, let's do 4 minutes, equals 3.5 times 4. Well, 3.5 times 4 is the same as 7 times 2 because 2 times 2. So I don't even have to like, see what I'm saying? 3.5 times 2 times 2. So anyway, it's 14. A little bit easier way of doing it. So 3.4 is 14. Okay. So now I know that this is a linear equation, so these should all make a line. So I'm going to draw my line. Here's my line. I'm going to draw my line in purple because I like the color purple. And if I did it right, they should all line up on this line. And then I can find out where it is on anything. But oh my gosh, look, this one is not on the line. Why not? Because I made a mistake. Do you guys remember how I intentionally made a mistake? This is how you can tell. This is where we do the does it make sense test because I didn't really notice. I didn't really notice that I'd made a mistake there because, okay, 3 minutes, we get 9 gallons. That's pretty close, sure. But then it's not on the line. So it's wrong. So I'm going to erase it. Boom, boom. What is it really going to be? So let's see, 3.5 times 3 is going to be 10.5, not 9. Now 9 is awfully close to 10.5. That's why I didn't set off my does it make sense radar, right? But it's not close enough. So then I go 3 and then 10.5 and boom, it's on the line. And that's how I know it's right. So I can look at this graph and go, okay, at 1.5 minutes, it's right at about 5.25 right there, right? 5.25 gallons. So you can look at the graph or you can do the math to figure out what the answer needs to be. And sometimes graphs are really, really visual, or nice to have like a visual of what's going on. So I'm not going to do your whole assignment for you. Don't you wish I would? But then you wouldn't learn anything. So Juan types at a constant rate. He can type a full page of text in 3 minutes. So how many pages of text? One page of text in 3.5 minutes. So how many want to know how many pages P he can type after T minutes? So the first thing you need to do is figure out what's his rate. How many pages per minute? We know he can do 1 page in 3.5 minutes, and that's great. But we need how many pages in 1 minute. So that's a division problem. Then you write the linear equation like I've done, and then you solve it and you graph it. You only have to graph one of these though. So, and then don't forget this one. It's like 1 on a page here because there's a whole problem here that I decided I didn't want you guys to do. So I erased it. You're welcome. So you just have 1 on there. Plus, let's kill all the trees. So then a train travels at a constant rate of 45 miles an hour. So we already have the rate. We don't even have to figure it out. So that's really nice. So what's the distance that the train travels in T hours? So you're going to give me that formula. We have a formula for the distance with hours. And then you're going to answer, how many miles will it travel in 2.5 hours? You just math that out for us, right? Water is leaking from a faucet at a constant rate of 1/3 gallon per minute. Holy freaking crap. This family is not going to have a good day. Okay. So 1/3 of a gallon per minute. Ooh, that's their rate. They already give it to us in rate, gallon per minute. We don't even have to do any math there. What's the amount of water W in gallons per minute that is leaked from the faucet after T minutes? So here you're going to write the formula. And then how much water is leaked after an hour? Oh my gosh, so much, like so much. This family's gonna come home. They're at the movies for like 2 hours. No, they're just gone for an hour. They went out to dinner and they're gonna come home and it's gonna be awful, people. I'm just gonna cry for this family. Anyway, and then a car can be assembled on an assembly line in 6 hours. I have no idea if that's accurate or not, but sure. Assume that the cars are assembled at a constant rate, so there's not any problems with the assembly. How many cars Y can it be assembled in T hours? So this is 1 car per 6 hours. Is that how we need it to be? No, we need it in cars per hour. So you're going to need to do some division there and get me a rate. How many cars per hour? If I can do 1 car in 6 hours, how many cars can I do in 1 hour? It's not going to be a whole car. That's okay. And how many cars Y could be assembled in T hours? So you give me my formula, Y equals rate times time, whatever the rate is. And then how many cars can be assembled in a week? Oh, well, how many? But there's a problem. My coat just fell. There's a problem. So this is given to us in hours, and we need this in weeks. Can we figure out how many hours are in a week? Now, we're going to assume that nobody goes to sleep. These are robots assembling this. Nobody goes to sleep. The plant's open 24 hours a day. How many hours are in a week? I don't know. Well, I know that there's 7 days in 1 week. And there's 24 hours in 1 day, right? Pardon my handwriting. Whew. So if I multiply these by each other, the days cancel. So I get 7 times 24, which I don't know what that is. 7 times 24 is 168. So I end up with 168 hours in 1 week. Kind of a nifty trick there. So, so we're going to need to know how many cars can be assembled in 168 hours. It's going to be more than 10, I bet. So anyway, there you have it. Let me know if you have any questions. I'm here, and I will see you later. Bye.